Okay, vector space. So if you have a textbook, then it's going to be chapter 4.1 to 4.3. As as I've told some of you when who have asked, you're only going to be test on material that we covered in class. So the textbook is much longer than what we can cover. So the chapters that I've not mentioned would not be tested. Okay, so we can start with a graphical representation of a vector, and typically that we're going to use two-dimensional real vectors. The reason is that with a two-dimensional real vector, you can draw it on a plane. Now you could draw a three-dimensional vector too, like you can draw a three-dimensional diagram, but that's probably the limit of what we can do in terms of drawing, right? So 4-dimension is very hard to draw. So we're going to use two-dimensional. We are going to use a two-dimensional real vector like this one. U is 2 equals to 2 and 3, right? Two numbers. If you want to draw it, you can draw it on the plane, right? With let's say U1 as the x-axis, horizontal axis, and U2 as the vertical axis. Then this vector can be represented by an arrow, right? This vector can be represented by an arrow pointing at the point where it takes on a horizontal value of 2 and a vertical value of 3. So that's how you graphically represent a vector of the arrow starting from the origin, because an arrow pointing towards a particular point, right? Now, the length of a vector is called norm, right? So it's just a name that we give it. So the norm of a vector is denoted by, as we can see, 2 vertical strokes on each side. So for real vectors, the norm is defined as the square root of the sum of squares, right? So you can see that what we have is the square root of u1 squared plus dot 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 plus un squared. So this is the definition of norm for real vectors. It makes a lot of sense. Let's say you have u equals to 2, 3 as we have before. Then the norm of this vector is going to be roots of 2 squared plus 3 squared, which is root 13. Now, can anyone tell me why this norm makes sense? You have learned this norm before. This is exactly how you would calculate the length of this vector. Why? This is the Pythagoras theorem, right? A squared plus b squared equals c squared. Right? The hypotenuse the hypotenuse length is a squared plus root of a squared plus b squared. So this actually makes a lot of sense. This is exactly how you would calculate the length in this case. Now, the norm might not be this simple in cases beyond real vectors. Right? This is for real vectors. This is what we have. But in more complicated cases, you might have a more complicated norm. But in this course, we only deal with real vectors. Okay, that's the length. How do you graphically represent vector addition? Let's say you have two vectors, u and v, right? They're pointing towards different directions. You add them up, 2, 3 plus 3, 1. You get 5, 4, which is this purple vector. So 2 plus 3 equals 5, 3 plus 1 is 4. So we have this purple vector, longer. How do we represent it graphically? You represent a vector addition graphically by joining them heads to tails. So you have in this case, I have u pointing towards the end of v, and then v pointing towards, and you can see that by joining the vectors u and v from heads to tails, you would result in the arrows pointing towards the same point at the end, right? The combination of these combination of arrows point to the same position at the end. And you can do this in the other way too, right? Instead of having U connected to V, you could have V connected to U, right? Now the head of V is connected to the tail of U, and once again you get the combination of vectors pointing at the same position as the purple vector. Right? So the graphical representation of vector addition is joining the vectors heads to tails. Here's another example. If you have, let's say you have a vector and you add that to the negative counterpart of itself, right? So you have 2, 3 plus -2, -3. Then the result will be 0, 0 because the two vectors, if you join them head to tails, you would just go back to the origin, 0, 0. So that's graphical representation of vector addition. Graphical representation of scalar multiplication. Multiply a vector by a certain number and you scale it up or down. So what you're doing is you're stretching the vector along the same direction, right? So in this case, you're multiplying the vector by 2, so the vector has lengthened along the same direction. And if you have a number smaller than 2, then it will be shorter. If you have a negative number, then it will go the other direction, but it would be along the same line. Next, something very interesting is that if you have two vectors that are perpendicular to each other, their dot product is 0. So let's take this example. You have U and V. They are 90 degrees from each other. U is 2, 0. V is 0, 3. You take the dot product, which would be 3 times 0, which would be okay, that's fine. Right, which would be 2 times 0 plus 0 times 3, then that's 0, right? So the dot product is 0. Now this is not dependent on the vectors being upright. Even if you have vectors that are at an angle, as long as the two vectors are perpendicular to each other, then the dot product would be 0. So in this case, you have x being 1, 1 and y being -1, 1. The dot product is 1 times -1 plus 1 times 1, which is 0. Right? So whenever two vectors are perpendicular to each other, the dot product will be 0. This extends to higher dimension. In the case of three-dimensional vectors, you might still be able to might still use perpendicular to describe what happened. But beyond 3 dimensions, you don't really use the term perpendicular because perpendicular is more of a graphical concept. Instead, we have this term orthogonal, which essentially means the same thing, right? So when the vectors are orthogonal to each other, then their dot product will be 0. So the concept of orthogonal really is just perpendicular when you think about it in a 2-dimensional or 3-dimensional situation. So orthogonal really conceptually is perpendicular, but it can appear in higher dimensional settings, right? So we call that orthogonal. Good. These are some of the properties that apply to vector addition and scalar multiplication for 2-dimensional real vectors. So what are some properties? Well, 1, if you add 2 vectors together and they are both 2-dimensional real vectors, then the result will still be a 2-dimensional real vector, right? This is expected, right? If you because the factor addition is defined element right. So if you add them together, then it's still a two-dimensional vector. U plus V is the same as V plus U, right? So you can, if you have three vectors, you can add them in any order you want. There. So if you add a vector to a vector of zero, of a vector of zeros, then you just get back the original vector, right? A vector added to the negative counterpart of itself would result in zeros. Multiply a vector by a number, then the result is still a two-dimensional real vector. If you multiply a number to the sum of two vectors, you can break apart the sum and do the multiplication first. If you have the sum of two numbers, then multiply to a vector, you can also do the multiplication first. Finally, two more. If you have two numbers multiplied to a vector, you can do the multiplication in any order. And finally, if you have one multiplied by a vector, then it's just the vector itself. Now, these properties are I think it's just very self-evident, should be true, given that factor addition and scalar multiplication are element-wise. So they are just true. What I want to do is to extend this concept beyond two-dimensional real vectors. So now, what I have is, okay, what did I just do? I replace every reference to two-dimensional real vectors space to a V symbol, right? All the R square becomes V. Now, everything remains the same if I literally just copy and paste, right? But I replace every reference to R square to V. Right now, what I have is this. Let V be a set of vectors. V is a vector space if the following properties are satisfied for every vector and within V and every real number C and D. So what I did is when these properties, which are really self-evident for real number vectors, apply to some other set of vectors, then we call that set of vectors vector space. Right? Now, these properties may not be that self-evident once you move beyond real number space. Real number vectors are easy for us to understand, but now we are talking about general type of set of vectors, right? V could be very weird, but as long as it follows these properties, then we call it a vector space. We call it a vector space. So vector space is defined by these properties. As long as these properties are satisfied, then that set of vectors is called a vector space. Now, so the idea of vector space is about being self-contained, right? When you add two vectors from the same vector space, the result is still within the vector space. When you multiply a vector by a scalar, by a number, then the resulting vector is still within the vector space. So it's self-contained in that sense. What might be some weird, relatively weird vector space? Take, for example, this one. Let's say you have a vector x1, 0, x3, right? And x1, x1, and x belongs to real numbers. Now, notice this example. This is a vector with three numbers, but it's not any three-dimensional real vectors, because in this case I am constraining the number in the middle to be 0, right? So x1 and x3 can be any real numbers, but x2, the number in the middle, is always 0. This is a three-dimensional vector. Now, the set of all such vectors, the set of all such vectors is the vector space. Because think about it, no matter how you add the vectors, let's say A0B plus C0D, that's just A plus C0B plus D, right? So when you do that, when you add two vectors where the number in the middle is 0, the resulting vector still has 0 in the middle. Similarly, you have E times A0B, that gives you AE0, AB, which once again still have 0 in the middle. So this factor with 0 for the second element, this is a vector space, and it's a weird looking one. It's a weird looking one, but it is a vector space because it's all the rules we list out here applies. All the rules we list out here apply, right? So that's why vector space could have many weird examples. We're talking about a set of vectors that is self-contained under addition and scalar multiplication. So what are some common examples? So here are some common examples. First, all real number spaces are vector space. So one-dimensional, two-dimensional, three-dimensional real number spaces, these are all vector space because regardless of how long the vector is, when you add two vectors up, it results in a vector of the same dimension, right? So next, polynomial spaces. Any set containing all polynomials of the same order or smaller is a vector space. Note that the all is necessary. You need to contain all polynomials of the same order or smaller. So the idea is this, right? Let's say you have 3x squared plus 4x, that's a polynomial of order 2. And then you have 5x squared plus x, that's also a polynomial of order 2. They are polynomial of order 2 because they both have x squared. Add them up, you get 8x squared plus 5x, which is another polynomial of order 2, right? So if you have a set of all polynomials of order 2 or below, then these three polynomials are all within that set. So it's self-contained in that way. Why does it have to be of the same order or smaller? Can you remove the all? Well, the problem is, let's say you have 3x squared plus 4x and then negative 3x squared plus x. Then when you add them up, 3x squared would cancel out with the negative 3x squared, resulting in a polynomial of a lower order. So the set of polynomials of the exact same order is not a vector space, because during addition and subtraction, you may very well lower the order of the polynomial. But it's impossible to raise the order, so you don't need higher orders. You just need lower orders. 3x squared would cancel out with negative 3x squared, and they are both polynomials of order 2. Right? So the set of all polynomials of the same order or below is the vector space because it's self-contained, but not if you just consider the set of polynomials of exactly the same order. Matrix spaces. Any set containing all matrices of the same size, because as we know, matrix addition and scalar multiplications are defined element-wise. So when you add two matrices of the same size, you get back a matrix of the exact same size. So that's self-contained. All right. So example. Now, if you want to verify whether a set of stuff, right? You want to verify whether a set of stuff is a vector space. You have to go through every single one of the 10 properties and show that they are true generally. It's easier to show something is not true than it's to show something is true. Because if you want to show something is not true, all you need is one counterexample. But if you want to show something is true, you have to show it for every single case, for every single property. So it takes more time. So in the case of real number, right, it's quite simple, right? You want to show whether a real number factorizes properly, right? Let's say you have A, B, C, D belong to real numbers, right? Then A plus B obviously is a real number. Now this is actually really easy to, like, it's almost trivial to show that a real number, a one-dimensional real number set is a vector space, because like A plus B is a number that is a real number. A plus B obviously equals to B plus A, right? So there's really nothing to do. So we would not ask you something this simple, because there's really nothing to show here, right? Right. So you just have to go through all of them, right? You just have to go through all of them. Right? These are all numbers, and these properties are kind of self-evident, so there's not much to do. Right? So let's just not do it anymore. So the concept is you have to do this for every single property, right? The example which I gave just now, the one where we have a three-dimensional vector with 0 in the middle, that one would take you more time to show, right? That one would take you more time to show. But the idea is the same. Go through the 10 properties, use symbols to represent the factors. Use symbols to represent the factors. Show that without substituting with any specific numbers inside, the properties hold. Then you can show whether the set is a vector space or not. Okay, so for real numbers, this is really trivial. Going back to the graphical representation, one thing I want to show you is that you can, if you have two factors pointing, now in the two-dimensional case, if you have two factors pointing towards different directions, they are pointing along different straight lines, then you can use these two vectors to reconstruct any vector on the plane. Take, for example, this one, 7, 7. And I have two vectors, u, which is 2, 3, and v, which is 3, 1. And I want to represent this purple vector with u and v. How do you do that? Well, you can do this. 7, 7 turns out equals 2 times u plus v, right? So 2 times u is 4, 6, plus 3, 1. That becomes 7, 7. So you can see graphically, the purple vector equals to 2 blue vector plus a red vector. Here's another example. Negative 1, 2. How do you represent negative 1, 2 by a combination of multiples of u and v? Here's how. You can have u minus v. That would give you negative 1, 2. This is general. This is something that you can always do as long as the two factors are pointing along different straight lines. So they must not be multiples of each other. In a two-dimensional plane, you need two vectors. In a three-dimensional space, you need three vectors. All vectors in the two-dimensional real number space can be represented by a linear combination of two vectors, u and v, pointing along different straight lines, and you can express that as in this way, right? Any vector w equals to a number c times u plus a number d times v. That's why it's a linear combination, because it's a sum. The terminology we use here when this happens is we say the two vectors u and v span the two-dimensional real number space. U and V span R square, right? U and V span the two-dimensional real number space. Equivalently, you can also say the set of vectors UV is the spanning set of the two-dimensional real number space, right? So it's a name. It's just a name. And as I've just mentioned, you can do this with any two vectors as long as they are pointing towards, they are pointing along different straight lines. Right? They cannot be multiples of each other. As long as that's true, you can always span the two-dimensional real number space with these two vectors. How do you find C and D? Like W equals to CU plus DV. How do you find the two numbers that you have to multiply to the vectors? Well, this is a linear algebra problem. You can use any tools that you have learned to solve it, like back substitution or Gaussian elimination. Take, for example, let's say I have a vector 7, 6, right? And I want to express that as a linear combination of U, which is 2, 3, and V, which is 3, 1. So 7, 6 equals to C times 2, 3 plus D times 3, 1. If you want to, you can express that as a simultaneous equation. You can solve this easily with back substitution. You get C equals to 11 over 7 and D equals to 9 over 7. For cases where you have higher dimension, you can use Gaussian elimination. Right. So it's a very straightforward linear algebra problem. In a three-dimensional case, you need three factors. Like, think about this. I don't know what it's called in English. What is it called in English? I don't know. Like this machine, right? This is something you see a lot in Taiwan and Japan, right? The way it works is, right? You see, you have a clamp. You have to, you control the clamp through these controls, and you want to clamp whatever you want and try to drop it. And if you succeed, then that stuff is yours. How many degrees of freedom do you have here? Strictly 3, right? The clamp can move left, right, back and forth, and up and down, right? This 3 degrees of freedom allows the clamp to cover the whole space within the machine. So this is a three-dimensional space, and you need three factors to span it, right? You have 3 factors here spanning the three-dimensional space, and you can see that's why you have 3 controls. These machines are real business anyway. Okay, so now the final concept I want to introduce today is called the concept called subspace. So subspace is a vector space on itself. Subspace is a vector space, but it's a vector space within another vector space. So a non-empty set W of a vector space V is a subset of V when W is a vector space under the operations of addition and scalar multiplication defined in V. Right. So subspace is a vector space. So you have a vector space. You have a vector space V, and you have another vector space W inside. Right. You have a vector space W inside. Okay, so the example is the one I gave you just now, the weird one. W equals to all three-dimensional vectors where the number in the middle is 0. This is a subspace of the three-dimensional real number space. Why? Because obviously any factor in W is a three-dimensional real vector, right? X is a real number. X1 is a real number, X3 is a real number, 0 is a real number. So any vector in this set is a three-dimensional real vector. It is self-contained. It is self-contained because as I've just demonstrated previously, if you no matter what X1, X3, X1 prime, X3 prime is, so no matter what the numbers are, add them up, you get back a three-dimensional vector with 0 in the middle. No matter what number you multiply to a vector in W, you get back a vector with 0 in the middle. So that's self-contained. But W is smaller than three-dimensional real number space because W only contains the vectors with exactly 0 in the middle, whereas the three-dimensional real number space contains all three-dimensional real vectors, including those that is not 0 in the middle, right? So W is the subset. W is a subset of V. W is a vector space. V is a vector space. So W is a subspace of V. Right? W is a subspace of V. Okay. Right. So in the case, once again, going back to the case of this 夾公仔機, any two dimension, any plane you form with just from two directions, right? Any plane you form from two directions is a subspace. So in this case, you can see the horizontal plane is a subspace of the three-dimensional space. The front-facing plane is a subspace of the three-dimensional space, and a cross-section is also a subspace of a three-dimensional space because it's self-contained, right? At any 2 points on a cross-section, add them up, it's still on the cross-section, so it's self-contained.